Hey, good evening, everyone. Gerald, are you with us? There he is. Oh, he's gone now. There, he came back. Hi, Gerald.
Yeah, hi there. Sorry about
so,
that.
that's okay. This is Rich
Watch.
Ozer, and we have Gerald McKeegan and John Curry, and welcome to
Hi,
another
everybody.
evening of the virtual, actually, the virtual telescope viewing.
Yeah.
Uh, this is the second time in recent weeks where we've had to have our virtual program held virtually. We are actually operating from our homes, from the comfort of our homes, except for Gerald, who's in New York City in uh, in the year
1998.
1998, yeah, something like that. And we're doing that, of course, to stay in compliance with the restrictions put in place by Alameda County and the state of California. We do have some news about upcoming programs, however, so this is certainly not a permanent state of affairs, but thought you should know that we're going to be running tonight's program from our homes, but we have a full program for you. A lot of interesting news from the week and a lot of astronomy. So, Gerald, we were going to start with the moon tonight, right?
Yeah, but before we start, I just want to remind everybody this month, Chabot is running a campaign to encourage people to donate and help support Chabot. Uh, right now the museum itself is closed to the public because of the pandemic, but we are still working, still doing a lot of programming like what you're watching right now. Virtual telescopes on Saturday nights. We have some Friday night programming that we do a couple of times a month. And we have a lot of daytime virtual programming that we're doing, especially for schools. And we're also doing some exhibit modifications and new exhibits coming in, getting ourselves ready to reopen sometime next year. So we do still need support, but because we don't have people coming up to Chabot, we don't have the income that we would normally have. So we are really pushing to encourage people to donate to Chabot. On the Facebook page, there is a donate button that I believe is above the comment section. You can also go to the Chabot website, chabotspace.org, and there's a donate button at the top of the page there as well. Now, there's something else we're doing this month, and that is a membership matching program. If you go to Chabot's website and you sign up to become get an annual membership, Chabot will match that with a free annual membership for a local teacher. So you get a chance to get your own membership and support a local teacher with it with their own membership as well. So we certainly want to encourage you to do that and help us out. Let us keep our programming going. All right,
Great, thank
on
you. Yeah,
to the moon.
to
To
the
the
moon.
moon.
To the moon. So, if you go outside right now and take a look in the sky over a little bit to the southwest, you'll see the moon. And the moon right now is a crescent moon. So I thought it would be good, even though we can't put the camera on the telescope, we have taken pictures of the moon in the past. And so I thought it would be good if we take a look at an image of the moon, the crescent moon, and kind of just take a little tour. And maybe you can go outside with binoculars, or if you have a small telescope, and see how much of what I'm going to describe to you you'll be able to see. So I'm going to go ahead and share my screen here for a second. Uh, I believe. Hang on just a second here. Make sure I got the image up.
And if you're looking for it, look out in the southwest, very
Right.
low in the sky right now.
Okay, where is it? That's interesting. Oh, there it is. Okay. All right. Here's the moon, the crescent moon. So this was not taken with our 36-inch telescope. With our 36-inch telescope, we would not be able to see the full disk of the moon like you're seeing here. We would see maybe this much of the moon at a time with our telescope. Our big telescope's pretty powerful, but its field of view is very small. So you'll see a lot of detail in that part of the moon, but you wouldn't see the whole moon. So this is taken with a smaller telescope, allows us to get the whole disk of the moon. And the first thing I want you to notice is the moon is not fully lit. Only a portion of the moon is lit. And if you look carefully and think about it, you can tell where the sun is based on how much of the moon is lit. So if you look at the moon right now, you can tell that the sun is somewhere over to the right. And that means that the moon in its orbit around the Earth, it's about not quite halfway around, going all the way around relative to the sun. So sometimes I've run into a misconception that the dark part of the moon here, this part here, is because of the shadow of the Earth on the moon, and that is not correct. What you see here is the part of the moon that's not lit by the sun, because right now the angle between the Earth and the moon and the sun is actually a little over 90 degrees. So we only see a portion of the lit part of the moon. Now, the other misconception is that the side of the moon that's on the other side between from the Earth is the dark side of the moon, and that's not true either. The moon gets dark and light all across the moon, just depending on where it is with respect to the sun. The far side of the moon is only dark in the sense that we can never see it. The moon is what we call tidally locked to the Earth, and that means we see the same face of the moon all the time. The moon's orbital period is about 29 and a half days relative to the sun. And it's and because they are also its rotation period is the same. So what we end up seeing is the same face of the moon all the time. Now there's some slight variations because the moon's orbit is not a perfect circle, it's an ellipse. So we do see a little bit of rocking back and forth, but we see the same face of the moon all the time. It's just that depending on the angle of the sun and the moon and the Earth, we'll see more or less of the moon's surface lit. So we are at the phase we call the crescent moon. And this boundary between the light area and the dark area, that's called the terminator. And you'll hear astronomers often talking about viewing things near the terminator, because if you look carefully, here's the part of the moon that's fully lit by the sun. And although you can see details, there's not a lot of contrast there. And that's because there aren't any shadows. But over here, near the terminator, you've got some long shadows in the craters and things, and that helps you get a sense of the depths of the craters and how high the mountains are and so on. So when astronomers look at the moon, we don't like to look at the moon when it's a full moon because the entire surface is lit. There aren't any shadows. We can't really make out details very well. We like to look at the moon when it's a crescent moon or a gibbous moon, and we like to look near the terminator because that's where we can really appreciate all the details. So I'm not sure how well this is showing up on Facebook, but I'm going to kind of give you a guided tour here just to get you oriented. If you've got a pair of binoculars, you can look at the moon and you probably see a view not too dissimilar to this. A small telescope would give you a similar view. And I'll just give you an idea of some of the features that you can see when the moon is a crescent moon like this. So up here, if you look carefully, there's two craters side by side right here. Those are the strong men. The one on the left is called Hercules. The one on the right is called Atlas. Let's see. And then down here, you see another crater right here that's kind of right on the terminator. And that's the crater Poseidonus. And Poseidonus is right at the edge of a large dark area called the Sea of Serenity. Now, you'll hear astronomers often talking about the seas on the moon, and you see a few of them here. Um, when you look with your naked eye at the moon, you see dark areas and you see light areas. And we sometimes imagine that the dark areas look like, the man in the moon or the girl in the moon or the rabbit on the moon. Different people see different things when they look at those dark features and light features together on the moon. But the dark areas are actually big, huge fields of lava. A long time ago, the moon was getting pummeled by asteroids and comets. This was like 3.8 billion years ago. And some of those asteroids were pretty big, and they made some pretty big craters on the moon. And at that time, the moon's interior was molten. It had liquid lava down deep inside. And those powerful impacts would crack the crust of the moon so that lava could ooze up through those cracks and eventually out onto the surface of the moon and fill those big, huge craters. And so that's what you see here is old impact basins and old low-lying areas that have filled with lava oozing up from those big impacts. And we call those dark areas, most of those dark areas, we call seas, or the Latin term is mare. And so the one that you can't see right here, that's the Sea of Sea of Serenity. And that little crater that you see right on the edge there, that is Poseidonus. Coming on down here, you see another part of another ocean right here, and that is the Sea of Tranquility, which is where the first Apollo landing occurred. In fact, the first Apollo landing occurred right about here, so just inside the Terminator there. And that was in 1969. Now, I want you to notice something. Notice how dark it is compared to, say, this area or this area. That's not just because it's close to the Terminator. That sea, Tranquility, is actually darker than the other seas around it because the lava in Tranquility has a higher titanium content. So that gives it kind of a bluish tinge. And if you take a really good color image of the moon, you'll actually see that there's a bluish tinge to that darker area in the Sea of Tranquility. And, if you ever decide you want to start a mining company and want to make a lot of money, there's lots of titanium up there, so you can have at it, right? Okay. Another kind of round area right here, another sea. This is the Crisium, the Sea of Crises. And it's just another impact basin that has filled with lava. And it's hard to see right now, but there's a little bright spot right here. And if you look carefully, it's a crater with a kind of a butterfly pattern of ejecta flying out of it. When asteroids hit the moon and produce a crater, all the stuff that was in the crater gets thrown out and often sprays out in distinctive patterns. And this is called Proclus, and the pattern of ejecta around Proclus is such that we can tell that when the asteroid hit, it came in at a very low angle from this direction, and it hit the moon right there, and then all the ejecta either sprayed out to the side or sprayed out in front of the crater, and there's no ejecta at all back in the direction that the asteroid came from. So that tells us it came in from a very low angle. Let's see, moving on down. This is another sea. It has a funny name, Kunda Tatus. And it's just another one of those basins that have filled with lava. Over here, right at the Terminator, you see a group of craters, and there's one crater here. I'm not sure if I can zoom in or not.
Yeah, hit that magnifying glass up on top.
Well, unfortunately, every time I go up there, the
Oh.
I can't
you gotta be real fast.
Yeah. Yeah, so I'm not sure whether I can zoom in this way. Let me try this. Nope, that doesn't work. Okay, well, I guess we're gonna have to live with it the way it is. So anyway, let me try one other thing here.
Yeah, you could try shrinking the window so you can get to the controls.
Well, I shrunk it too much there.
While you're doing that, let me take a quick question here. There's a few that have been answered already on Facebook there, though. But one of them is one of the observers is, as he looks at the Terminator, it's going more east and west instead of north and south. That's just because of the direction that you're looking at it versus this photograph. This photograph is actually on its side a little bit. So where the moon is tonight, the Terminator would be more horizontal than this image shows.
All right, there we go.
You did it.
Hey, well.
Now you lost it. You undid it.
I give up. let me go. Is that a little bit bigger?
Not really.
Okay, well, forget that then. All right, well, anyway, what was I talking about? Oh, yeah, these craters right here. You look at this crater right there and you see it's got a kind of a central peak to it. That's the crater Theophilus. And right next to it, actually, it overlaps the crater Cyrillus. And Theophilus has that big central peak. That's called a rebound peak. And often when bigger asteroids hit the moon, they produce craters with rebound peaks. And what happens is they hit the ground and they actually compress the ground in the center of the crater a little bit during the impact. And then once the energy is dissipated, the ground rebounds back up. At the same time, all that material that was thrown up onto the rim of the crater, some of it slides back down into the middle of the crater. So those two things, the rebound plus the slumping of material from the rims, produces that central peak. And you see that mostly on larger impact craters on the moon. Small craters made by smaller asteroids are just bowl-shaped and they don't have a central peak like that. So Theophilus and Cyrillus, now if you look carefully, you can see that Theophilus kind of overlaps Cyrillus. And that tells us that the impact that produced Theophilus occurred after the impact that produced Cyrillus. And before we were sent astronauts to the moon, before we had samples from the moon, we tried to age the moon by looking at craters to see which craters were on top of what other craters and trying to judge relative ages of craters based on which ones overlapped or within other craters. And there were a lot of astronomers who spent a lot of time, especially in the 50s and early 60s, doing that. Once the astronauts went to the moon and took samples from 6 different locations and were able to date those samples, then they had ground truth that they could use and say, okay, now we can know how old these craters are. And of course, the craters are all millions or billions of years old. It is very common to see craters on the moon that are 1 billion years old or more. And that's because the moon has no atmosphere, it has no plate tectonics, it doesn't have weather, it doesn't have plant life or animal life, nothing to reshape the surface except those impacts. And so an impact occurs and the impact crater stays there literally for billions of years. So, people often wonder, well, why is it that we don't have all these craters on the Earth? Is the moon protecting the Earth from impacts? Actually, the moon is very small compared to the Earth. It doesn't protect us at all. In fact, we have 16 times more impacts on the Earth than we do on the moon. But the Earth has plate tectonics, it has weather, it has rain, it has rivers and oceans and plant life and animal life and those funny two-legged creatures running around. And all of that reshapes the surface of the Earth and basically buries the craters. So craters on the Earth only last maybe a few tens of thousands of years or hundreds of thousands of years, but then they fade away because of all those other processes. So anyway, moving on a little bit here, a couple of more things I want to point out to you. This region here is called Nectaris, the Sea of Nectar, and then the crater down here, that's Fracastorius. It's another crater right on the rim. And again, when you look at it, you can see it's filled with lava, but you can tell that it occurred after the impact that produced the Sea of Nectar.
Hey, Gerald, try hold your control key down and use your mouse wheel.
I don't have a mouse wheel.
Oh, gosh. I know what I'm getting you for Christmas. A mouse wheel.
Well, I'm
just the wheel.
I'm sure I could connect a mouse to this, except that I've run out of USB ports.
All right.
So anyway, last thing I wanted to point out was down here. If you look carefully, it looks like Mickey Mouse ears down here. Can you see that feature right there? And that's a group of three craters. The one up in the left is called Pitiscus, and this is called Vlach, and the bigger one is called Homo. So those three craters, when you get the light just right, it looks like Mickey Mouse ears. So anyway, that's the moon. If you go outside tonight or even tomorrow night, the moon will look very similar to this. And like I say, you can use a pair of binoculars, and maybe you can find some of these features. All right.
Hey, Gerald, I got a request from someone. I'm going to actually take control of the screen here for a second, because somebody on the YouTube channel asked to see a picture of the far side of the moon. Hold on for a second. I do happen to have one.
Race car WRX asked for that.
Yeah. So can you guys see that?
I can see it.
Yeah. Okay. Good. So anyway, that's a photograph of the far side of the moon, and I know that we have upset a lot of Pink Floyd fans tonight because there is no dark side of the moon.
Yeah.
Sadly.
But that's all right. They know that at the end of the song, you can hear the guy saying, "There is no dark side of the moon."
That's right. That's right. At the end of the song, he does say that. I've forgotten about that. And
there is. There is a dark side, but it just changes every day.
That just changes every day. Right.
Yeah.
The far side of the moon is remarkably different from the close side.
Yeah.
There are a much larger number of medium to small craters, and there's far fewer mare features, and they're all consolidated really in the upper right quadrant of this photograph. I don't know if you wanted to speak to why that is, Gerald, or if there's any theories.
You saw those big dark areas, and if you saw a picture of the full moon, you'd see there's quite a few big dark seas on the near side of the moon, the side that faces us. And those were caused by very large impacts. And those large impacts left concentrations of mass below the surface. Astronomers call them mass cons. And so for whatever reason, most of those big impacts occurred on one side of the moon. There are some theories about why that happened. There's some talk about the possibility that we once had two moons and things like that. But so you have a lot of mass cons on one side of the moon, and those mass cons get tugged a little harder by the Earth's gravity. You know, the reason the moon is in orbit around the Earth is because it's the Earth's gravitational field and the moon's gravitational field. They're pulling on each other, but the orbital velocity is such that the moon orbits around. And because the Earth's gravity pulls on those mass cons a little more than it does other features on the moon that eventually cause the moon to stop rotating with respect to the Earth. And that's why we see the same side of the moon all the time. Uh, Tidal locking is actually pretty common. There are a number of moons of other planets that are tidally locked as well. Um, and especially for planets like Jupiter and Saturn that have very strong gravitational fields. So another interesting thing is we didn't see it because it's right now in the dark side of the moon. That's the very large impact basin on the near side called the Imbrium Basin. It's a huge impact basin. And that impact basin occurred basically, if you imagine on the other side of the moon, right where, oh, you can't see my arrow, never mind. so it's kind of in the north central part of the moon when we view it from Earth. And that impact was so powerful that it created a shock wave that went out in all directions from the impact and went around to the other side of the moon, and all the shock waves all came together on the other side of the moon. So it's kind of hard to tell, but there's a jumbled area right here, and that's where all the shock waves came together from the Imbrium impact.
Are you talking about
jumbled all the three.
this lower left quadrant?
It might be. I'm not sure what the angle is here. Is this may be part of the near side of the moon right here? So it would be over. It would be over
more
this
like
area.
that. Yeah.
Right. So you know, if you study this in more detail, you can actually tell where those shock waves from the Imbrium impact came all the way around the moon and concentrated in one part on the opposite side of the moon. So,
very cool.
right.
Yeah, thanks.
Yeah, some more questions. Margot wants to know, what are the most common elements on the moon? That's a good question. But
that's a good question because it goes to the question of how did the moon form? When you look at the composition of the moon, it resembles very much the composition of the Earth's crust. And one of the characteristics is that it doesn't have a lot of iron in it. Now, the Earth has a lot of iron. Of course, it's all near the center of the Earth, but the Earth has a lot of iron in it. And the moon has much less iron, and its composition is more like just the Earth's crust. So you got silicate rocks, a variety of silicate rocks. There's things called plagioclase, which is a type of rock that has manganese, and it's got aluminum and silicates and so on and so forth. The typical rock components that you would find at the surface of the Earth, on the Earth's crust, but it doesn't have the composition, the same relative abundances, because it's mostly crustal material. And that tells us that the moon formed from something that had caused the crust of the Earth to be knocked off and recombined to form the moon. And that's where the theory came up that the moon was formed by an impact about 3.5 billion years ago with a protoplanet we call Theia. And we think what happened is, in the very early history of the solar system, there were more planets, and there were a lot of small planets that were still in the formation process. And one of them, a planet about half the diameter of the Earth, roughly the size of Mars, hit the Earth and shattered that planet, and also ripped off a big chunk of the crust of the Earth. And eventually all that material went into orbit around the Earth and reformed and became the moon. And that theory explains why it is that the composition of the moon is more like the Earth's crust rather than the same composition as the the total Earth. Before that theory came about, there were a lot of other theories about how the Earth formed, and none of them could really explain the composition of not the Earth, the moon formed, but none of them could really explain the composition of the moon. One common one was that the moon and the Earth formed at the same time out of the same material. If that was the case, the relative ratios of all the different elements should be pretty much the same, and it's not. So they had to come up with another theory, and that's where the impact theory came from.
All right, thank you.
Right.
We're getting
Sure.
a lot of questions, and people very interested, of course, in the upcoming conjunction. And I know we had kind of an order in which we were going to do our program tonight, but maybe we should skip ahead to talk about that a little bit, because a whole bunch of people are saying, show us Saturn and Jupiter, please, please.
There's big interest in it.
And I think we could talk about what our program is going to be on Monday, and maybe show a couple of photographs that we've acquired of the upcoming of the conjunction.
Yeah.
You mean to tell me that people?
Go ahead.
I'm sorry. You mean to tell me that people think the conjunction of Jupiter and Saturn is more important than looking at the moon? Okay, so
it has been mentioned that Jupiter and Saturn are now already set. It's late, but don't forget we're not at the telescope tonight, so show photographs.
Yeah, pretend this is Jupiter and pretend this is Saturn. And no, we do have some photographs. We do have some photographs.
Yeah, we got some photos and a little explanation of what's going on. So for those of you who don't know, I don't know where you've been for the last few weeks, but
not here.
Saturn and Jupiter are getting very close together in the sky. So if you were up a little earlier looking outside, say right after sunset, you probably saw in the southwestern sky two what you may have thought were stars very close together, one brighter than the other. And those are actually the planets Jupiter and Saturn. Now, Jupiter orbits around the sun faster than Saturn does. Jupiter takes about 12 years to orbit the sun. Saturn takes about 30 years to orbit the sun. And because of that, about every 20 years, Jupiter laps Saturn. And when that happens, from our point of view, Jupiter and Saturn appear very close to each other in the same part of the sky. They're physically not close to each other. In fact, they're going to be about 420 million miles apart here on Monday. But they appear in the same part of the sky, usually not so close together that you can't distinguish that there's two objects there. But this year, we're going to have an unusual conjunction when the two of them are very close to each other, when they're lapping each other. And this year, they're going to be so close together from our point of view that they will almost appear to be one object. And so that's getting a lot of attention, and that's going to come up this coming Monday. We're going to start viewing it at about 5 o'clock with our 36-inch telescope. So we will be up at Chabot, but you'll notice when you watch that we're going to be following some very strict procedures so that we remain COVID safe. But we will point the telescope at the two planets starting at 5 o'clock. They will be so close together in the sky that both planets will appear in the same field of view of the telescope. So I've got some images that I can show here. Bear with me just a second.
In the meantime, let me make a quick explanation here. We've got a question about thinking that we were actually looking through the telescope tonight. No, we're stuck at home. We're not able to go up to Chabot tonight. So we're doing this from home, and we're just using photographs that we've previously taken with our telescopes.
Right.
But we're doing
Right.
such a good job. We fooled you.
Yeah. Okay, so here's an image that kind of shows you what's been going on. Back in October and earlier this year, Jupiter and Saturn were pretty far apart in the sky. But as the Jupiter gets closer and closer to Saturn, because it's orbiting faster, they've been getting closer together. But at the same time, the Earth has been orbiting around the sun over the last few months. And so the position of the two planets has been changing from night to night. They've been moving farther and farther towards the western sky. And on Monday night, they will be low in the southwestern sky right after sunset. And they will appear to be almost close together. In fact, I've got an image here. Here's what they'll look like in the telescope. Let's see, I think I have another image. No, I don't. Okay. This is what they'll look like in the telescope. Now, this is an animation. This is not an actual live image, but we'll be able to see both planets in the field of view of our telescope so close together that they both fit in the same field of view. And
let me steal. I'm going to steal the screen share here.
Okay.
And show a couple pictures from tonight.
Oh yeah, and, some astronomers have already been taking pictures.
Yeah. So here's the first one. This is from Dave Shaw, and he snapped this quickly up at Lake Almanor, and I stole it off of Facebook. I didn't ask him permission, but he won't mind.
Yeah, so you can actually see a couple of Jupiter's moons there.
Yeah,
too.
Here's some of the moons and a little bit of the rings, and this is from a friend in Texas, Mike Jones. And he's got the Galilean moons there very prominently displayed. And here's Saturn, of course. And of course, these are going to be even closer on Monday night. So that's kind of, what we're anticipating. So that's a nice sharp image.
Yeah. Now these pictures are taken with small telescopes that have very wide fields of view. So they're already able to get both of them in the same field of view. Our telescope, our 36-inch telescope at Chabot, has a very narrow field of view, but they're going to be so close together that they'll be in the same field of view, even with our big telescope. All right. So I got one other image to share here about this. Go back to my animation image and just kind of to explain what's going on. So this is viewing the solar system from above. And no, this is not a live image. This is just an animation. And you see Jupiter's orbit here, and you can see Jupiter is closer to the sun than Saturn is, all right? And what's happened is because Jupiter orbits faster than Saturn, periodically it passes between Saturn and the sun and basically laps Saturn. And what's happened now, here's the Earth down here, and you can see that they're all lined up. And so that's what's going to be happening. From our point of view, the two are lined up, even though Jupiter technically has already passed the point where it's directly between Saturn and the sun. It has now reached the point where it forms a line with Saturn and the Earth. And so that's what we call a conjunction. Now, this happens, like I said, every 20 years or so, but most of the time, they don't get nearly as close together. And that's because the orbits, although they're shown here as being parallel to each other, they're actually not precisely parallel to each other. They are at slightly different angles to each other. So sometimes the conjunction, they're much farther apart. Sometimes they're closer together. The last time they were this close together was in the year 1623. So almost 800 years ago. And in fact, at that time, they were actually closer than they're going to be tonight or Monday night.
Gerald, a good question here. Is there a gravitational effect on Jupiter and Saturn as they get closer? or are they still too far away from each other?
Well,
there's always some kind of gravitational effect. However, yes, they are very, very far apart.
Yeah, they are far apart, but they do have a gravitational effect on each other. Both of them have very strong gravitational fields. So when they're lined up like this, we feel the gravitational field of both of them. So we're actually being tugged on very, very slightly by the combined gravitational fields of both Jupiter and Saturn. In fact, if we were to get rid of the Earth and get rid of the sun, and just float out here in space without either one of those, we would eventually end up on Jupiter. So that's how strong the gravity is. So even though it's way far away from the Earth, we do feel on a very slight basis the gravitational pull of both the planets. So, and they do affect each other as well, but very, very slightly. It takes a long time for you to really notice any difference, like thousands of years. All right.
Mm-hmm.
Okay. Well, so we reordered our presentation here.
We did. We just had to satisfy all of those conjunction people.
Right.
So
yeah.
Hopefully we can do a better job Monday.
Yes.
Yeah, as Richard said, we will be looking at it Monday with our big telescope, and we will be live streaming those images, and we'll try to do it as long as we can. Our big telescope has a limit, though. It can only go down to 15 degrees above the horizon, and that's to protect the telescope. So we estimate that sometime around 5:40 or so, we may hit our telescope limit. So at least for about 40 minutes or so, we're going to be able to view it. So you definitely want to get in and watch while you can. Looks like the weather's going to cooperate with us. So tune in 5:00 p.m. Pacific time.
Very important. do not set your alarm clock for 3 a.m.
Yeah. 5:00 p.m. It's nice time of the day. 5:00 p.m. Pacific time on the Chabot Facebook page, and I guess we're going to do it on YouTube as well, right?
That's correct, as always.
Richard.
Yeah. Yes.
Okay. So on Chabot's Facebook page and our YouTube page, and we'll stay with it as long as we can. All right.
Great.
Okay. What's next?
Next, you have some images from Nellie's past to share with us of the current night sky. And
oh yeah. Well, let me get rid of some of these other images that I got up here, and
yeah, you're gonna get lost in all your images there.
Yeah. Oh, where should we start? How
about M1?
M1. Okay. Yeah, sure. Bring that
Start at the beginning
here.
with 1.
Yeah. Right. Yeah.
What a crab.
Yeah.
So this is an image of a cloud of gas and dust out in space. We call M1. It's also known as the Crab Nebula. I have no idea why they call it the Crab Nebula, because it doesn't look anything at all like a crab. But it's actually the remnant of a supernova explosion. So at one time, there was a massive star at this location out in space. That star got old, and eventually it blew itself up in what we call a supernova explosion. And a supernova explosion blows the remnants of the star all over space, literally throwing them hundreds of light years out into space. This particular event was actually observed from Earth in the year 1054 is when the supernova occurred from the perspective of those of us on Earth. And it was so bright that they could see it in the daytime. So they recorded it as the appearance of a new star. And like I say, it was bright enough to see in the daytime. It wasn't until years, or actually centuries later, that we connected this fuzzy patch in the sky with the record of that event in 1054. So this is a supernova explosion. Now, a lot of people think, well, all stars die in a supernova explosion. That's not the case. Most stars actually do not die in a supernova explosion. They die in a very slow process that produces what we call a planetary nebula. It takes hundreds of thousands of years for this process to go on, and the star just slowly blows all its outer layers off, and then it collapses into what's called a white dwarf. And I've actually got an image of a white dwarf surrounded by gas. So if you'll bear with me here for just a second, I'll see if I can switch to another image here somewhere. I thought I had it. Oh, there it is. All right. Okay. So here you see a faint kind of greenish, bluish, turquoise colored cloud of gas out in space. We use the word nebula to describe these objects. And the word nebula just means cloud. And so it can be a cloud of gas, a cloud of dust, anything that looks like a cloud out in space, we'll call it a nebula. This particular one is called the Clown Face Nebula. If you could zoom in on it like the Hubble Space Telescope does, you would see that there's actually a kind of a reddish orange patch right in the center, kind of like a clown's nose. And so that's where they came up with the Clown Face Nebula. And this is the remnant of a dying star. This is a star that dies by the more common process. It's a star that was once similar in size to our sun. As it grew old, it swelled up, got to be 100 or more times its original size, and then started losing its outer layers, producing a strong internal wind that blew its outer layers out into space. And that went on for tens of thousands of years, maybe even 100,000 years. And it eventually lost easily half its mass, blown out into space. And in the meantime, the fusion process, which is what drives the star, the fusion process eventually stopped. And so whatever was left of the star collapsed and became what we call a white dwarf. White dwarf is all the remaining mass of the star compressed down into a ball about the size of the Earth. It's extremely dense. And I read a thing the other day here that said you could, if you took just enough of a white dwarf to stuff into a matchbox, the matchbox would weigh 100 tons. So it's very dense material. And it is surrounded by all the gas that was expelled by the star when it was that red giant star. And the white dwarf, because it's so compact, it's extremely hot, and it generates a lot of ultraviolet radiation, which goes out and it hits that cloud of gas surrounding the white dwarf, ionizes the gas, and causes it to glow. So what you see is the glowing gas that was expelled by the star, and there's shock waves within the cloud of gas. And right at the center, actually, this white patch is not the white dwarf. That's just because it's so bright there, it saturated the camera. But right at the center is a very faint little dot that is the white dwarf. It's all that's left of what was once a star like our sun. And this is a preview of what will happen to our sun in about, 5 or 6 billion years. All right. Okay, I got quite a few other things. How are we doing on time here? It's
we're at
9:49.
We got a request to talk about meteor showers. Unfortunately,
too late.
The questionnaire should have talked to us last week.
Yes.
Take a look at our shared video from last week, and we talked all about the
Yeah, we do.
Geminids.
Yeah, we have quite a bit of information on that one.
Yeah, for those of you who don't know what we're talking about, last on the 13th and 14th, I think night of the 13th and the morning of the 14th was the Geminid meteor shower, which is an annual meteor shower. It's one of the most prolific meteor showers around, and that occurred, like I said, on the night of the 13th into the morning of the 14th. And I understand quite a few people saw some pretty good meteors that night.
Yeah.
So,
yep.
And we do record these sessions, so you can go back and look at older versions of them, and you can go back and look at last week's session if you'd like, and revisit it.
We talk a little bit more about it. Yep. Yeah, we don't actually show you the meteor shower, but we do talk about it. Okay, so I got another image I wanted to show you here. Just some other objects up in the sky. If you look towards the eastern sky, about a little more than halfway up from the horizon, you'll see this faint little fuzzy cluster of stars, and that is called the Pleiades. The Pleiades are a group of stars that all formed from the same cloud of gas and dust. And most of that gas and dust is now dissipated, leaving behind all these very young stars that formed from the cloud. They all formed at about the same time as that cloud was condensing. And this is how new stars form. Our sun formed in a very similar process a long time ago. It was a part of a cluster of stars that formed within a condensing cloud of gas and dust. And we see an example of this. And this is actually a naked eye object. You can see it with your naked eyes. It's small. It looks like a little faint little grouping of stars in the constellation Taurus. And it's about not quite 400 light years away. Now, what's going to happen is these stars are orbiting around the galaxy, but because the distance between the center of the galaxy and individual stars in the cluster are not exactly the same, the stars that are a little bit closer to the center of the galaxy orbit a little faster than the ones that are farther away. And because of that, over time, the stars are slowly going to separate from each other, and eventually it will no longer look like a cluster of stars. They will just all be in different parts of the sky. But this is a very common process. We call this an open cluster, and there are quite a few of them out there. Most of them you need a telescope to see, but the nice thing about the Pleiades is you can see it with your naked eye. Now, the Pleiades is the name given to some sisters in Greek mythology. So we often call this cluster the Seven Sisters. But in Japan, this cluster is called Subaru. And if you look at the emblem on the front of a Subaru car, it's kind of a graphical rendition of the six brightest stars in the Pleiades. And that actually represents, I think, John, you told me it was the six companies that merged together to form the Subaru company.
Yeah, I believe that's right.
Yeah. All right. So this is called the Pleiades. It's out there. And like I say, you can see it with your naked eye. All right. Okay, I got a couple other images that we can look at here. Bear with me. Oh yeah, this guy. So if you look low in the eastern sky, actually it's getting up a little bit higher now. If you look in the eastern sky, you will see the constellation Orion. Orion is one of the most easily identified constellations in the sky. It's very large constellation, and it has more bright stars than any other constellation in the sky. And also, it's got three stars that are nice and evenly spaced in a line. And so the constellation is very easy to spot. Those three stars we call the Belt of Orion. And if you look carefully at the belt of Orion, below and a little off to one side, you'll see a much fainter string of stars. And the center of that string of stars, the stars are kind of fuzzy. They don't look real distinct. And that's because it's actually not a star. It's actually what we call the Orion Nebula. And the Orion Nebula is a huge cloud of gas and dust about 1,300 light years away, where new stars are forming. So this is a quickie image that I took one day using the telescope, the 36-inch telescope at Chabot. And you can see this huge cloud all around here. And if you look carefully, you can tell there's a pocket right here. So this is a kind of a finger of cloud that's in front of the pocket. And then this is the bubble within the pocket of clouds there. And then you see these stars here. We call this the Trapezium. And the Trapezium is a group of very hot, very young stars that formed from the cloud. Stars are forming within the cloud. A minute ago, we looked at the Pleiades, and I told you that was a group of stars that formed in a cloud. This is the actual process as it's happening. So these stars here are very massive stars. They're extremely hot. Massive stars that burn very hot don't last very long. So these stars won't be around. You come back here in 10 billion years or 10 million years and they won't be there anymore. Whereas our sun is already 4.5 billion years old and will last at least another 5 or 6 billion years. But massive stars don't last very long, but they put out a tremendous amount of light and energy. So much so that the energy from these stars is actually pushing the cloud away. So these stars formed within the cloud, but then they started producing so much energy that they actually pushed the cloud away, producing this pocket around the trapezium. Now, some of the light that you see in the trapezium is reflected light from those stars. But some of that light is also emitted light. Those stars emit a lot of ultraviolet radiation. Ultraviolet radiation goes out and ionizes the gas in the cloud and causes the cloud to actually glow. So you're getting both reflected light and emitted light from the cloud. You notice there's quite a bit of redness here that tells us there's a lot of hydrogen in this cloud, which is typical. Most of these big clouds out in space are composed mostly of hydrogen gas with other much smaller quantities of other gases and dust and so forth. So this is the Orion Nebula. If you're in a dark sky location, you can easily see it with a pair of binoculars, and you might even be able to get hints of it with the naked eye, but definitely with a pair of binoculars, you can see the Orion Nebula, and with a small telescope, you can actually see a lot of detail. It's one of the easiest deep sky objects to see with even a small telescope, all right? And again, it's about 1,300 light years away. All right, how are we doing on time here?
Yeah, I got a few more minutes. Do you want me to?
Any questions that we need to answer?
Yeah, I think we're caught up on questions. Jasper wanted to know what object this was. I let him know it was M42, and let's see if there's anything on YouTube in the way of questions.
Then you had something you wanted to show, right?
Yeah, I do. We had another significant astronomy event in the past week. It just wasn't in a place where we could see it here. And what I'm going to do is share my screen. Give me a moment here. Here we go. So we had a total eclipse of the sun in the last week. On the 14th, there was a total eclipse of the sun that was visible from Argentina and then, of course, in the ocean. Now, in a normal year, a bunch of us probably would have had friends or maybe ourselves flying down to Argentina to try to catch the 2 minutes of totality. This was not the year for that, and not very many people I know even made the attempt. But this eclipse was a 2 minute and 10-second totality. And it was about at 1:15 or so in the afternoon in Argentina. And let me see if I can get some of these other photos.
And Chile.
Show up. And Chile, that's
Yeah,
correct.
yeah.
Chile over here and Argentina over here. And that's a photograph of the eclipse. And what you're seeing here is the moon is blocking the view of the sun, but around the moon you can see the sun's corona, and the corona is an extremely hot part of the sun. In fact, it's the highest temperatures measured in the sun, much hotter than the sun's surface, and it's basically ionized gas plasma that is radiating away from the sun, and it's only visible to people on Earth when we have a total eclipse. We do have spacecraft in orbit around the sun that have a mask in front of the camera that simulates an eclipse so they could study the corona. But from Earth, from the normal viewing on Earth, the only time you could see the corona is during a total eclipse. And every total eclipse has its own fingerprint, so to speak. And the corona looks different at every eclipse depending on what the nature of the magnetic field around the sun is at the time. If the sun is very active, that corona appears very different than at times when the sun is much calmer, fewer sunspots, fewer prominences. And this eclipse is very different from the last one that I saw, in that the corona is very evenly distributed around the sun rather than sharp points. That's kind of neat.
One other thing I wanted to point out, if you look up at about the 1230 position near the top, right there, you see how bumpy it is?
Yeah.
And then if you look down at the bottom, you see some bumpiness as well.
That's the moon.
The moon.
Yeah.
The moon has got mountains and craters and all that good stuff. And when you get a total solar eclipse like this, you can actually see that bumpiness that's on the moon. And sometimes you get this really cool effect called Bailey's beads. And it's because just before or just after the two are perfectly lined up, when they start to kind of unlined up, the sunlight starts to shine through the gaps in the mountains, and it produces these little bright flashes along the rim, which we call Bailey's beads. And it's because of the sun shining through the gaps in the mountains on the moon. It's a really cool effect.
It is. All right. I wanted to show this. Probably the best view of the eclipse was from the GOES weather satellite. And you can see the I'm going to I have to play this over and over again. You can see the shadow going from west to east here and ending just before it hits the coast of Chile. There we go.
That's a neat photograph.
It is.
Yeah.
Well, that's the satellite I always use to predict weather that's going to hit the west coast a week out,
Right.
And the last photo I wanted to show is that during this eclipse, there was a discovery of a comet that
Soho.
For the one on the photo on the left is from SOHO, which is a spacecraft that's in orbit around the sun, and it has what I was talking about, the mask that blocks the sun so that we could study the sun's corona. But right over here, there's a little dot, and that was a comet, and here it is blown up, magnified several times to make it more visible. But there is a photographer, Andreas Moller, down in South America, who managed to capture it with his telescope. And here's the comet, and there's the magnification of it, and there is the sun's corona with the eclipse. So I thought that was a really interesting photograph. And that's all I got on the eclipse, I think. No, that was something else.
Oh,
I can show that too. Yeah, might as well. This was another image from South America. This is a photograph from the observatory complex in Chile in the Atacama Desert. And they have a fisheye lens on a webcam. And this is a photo from a couple of weeks ago. And you get an amazing view of the sky. It took me a while to figure this out. I had to kind of study it for a bit, and I even got Gerald's help before we started the program tonight. So what we got is the large and small Magellanic Clouds, which are not visible from where we are. You have to be in the southern hemisphere to see those. And these are dwarf galaxies that are just adjacent to the Milky Way and very prominent in the sky in the southern hemisphere. Here's Mars, right there. Here's the Andromeda Galaxy, our largest nearby neighbor, all the way in the north. And here's Jupiter and Saturn, right there. And we decided, this is where I got Gerald's help. We decided that this was Aldebaran. And this is the Hyades cluster over here. And here's
that's
the Pleiades,
Pleiades, yeah.
right there where my pointer is. So anyhow, I thought this was very unique. I had never seen a photograph that included both southern hemisphere and northern hemisphere objects at the same time. And I thought I would share. That's what I got.
Pretty cool.
Yep.
So I see a picture from Mark. He says the Breakthrough Listen team reported that they found an interesting radio signal coming from the direction of Proxima Centauri, but he says it's probably too soon to jump to any conclusions. Yeah, you're right. There are many reasons why you get radio signals. You know, we use radio telescopes because all kinds of objects out in space emit radio waves. I would have to see what that radio signal looks like. Does it have a pattern to it? Does it have anything that would indicate that it's other than just radio noise, typical of what we get? You know, if you point a radio telescope at the sun or a radio receiver at the sun, you'll get noise, radio noise, because the sun is emitting radio signals. It's just totally random. So I would want to see what that radio signal looks like before I would jump to any conclusions about.
Well, just in case, stock up on water and apparently toilet paper.
Toilet paper, right?
Yeah, right.
That's the closest star to our sun, so we ought to just take a trip down there and see.
Yeah, right. It's 4 light years away. So none of us are going there. So,
right.
So anyway, yeah, it'll be interesting to see, you know, what other information comes out of that report, what the radio signal looked like. Does it have any kind of a repeating pattern to it or anything that would suggest that it's other than just plain old radio noise from a star.
Let Jodie Foster take a listen to it.
There you go.
That's right. Where's Jodie Foster when we need her? That's right. All right.
All right.
What do you think?
Yep.
After 10?
Yeah.
I want to remind people that next weekend we're taking a break. We are not going to have a virtual telescope session on Christmas weekend. We will be seeing you again the first Saturday night of 2021.
January 2nd.
Yeah,
January 2nd. Right.
Farewell 2020.
Yeah,
right?
Good riddance.
Good riddance. And we will see you in 2021. And please tune in on Monday afternoon and join us for the close conjunction. And I guess that's it. You guys have anything else?
Well, and don't forget, you know, again, support us in any way you can. Click on that donate button on the Facebook page or go to Chabot's website, chabotspace.org. and click on the donate button there, or you can sign up for a membership and you'll help out a local teacher if you do that. We'll give a free membership to a local teacher for any membership that gets signed up this month. So help us out.
Yeah.
All right.
All right. Well, good night, everyone. Merry Christmas, Happy New Year, and all that good stuff. So we'll see you soon.
See you next year.
All right.